Okay, so we're happy to have Joshua Stuckey here virtually at Rutgers from KSU, and he'll be talking about elementary estimates for smooth numbers. Thanks.
Yeah, for sure. Well, thanks so much for inviting me. I always love talking with you all. So this is a pretty informal talk. I have not spent a lot of time on these slides or practicing. So if I stumble over myself, kind of forgive me for that. But basically, I've been learning about smooth numbers recently. They've kind of come up as something that I wanted to learn about, and kind of I had some questions that I think would make good research questions, but I kind of needed to learn about smooth numbers. And so in the process, I've learned some really cool elementary arguments, mainly due to Hildebrand and Bruijn. I don't know if actually know if that's how you say his name. But anyways, the elements are really, really nice. The arguments are really nice. And I just wanted to share them with you guys because I think they're cool. So that's what I'm going to talk about today. First of all, what are smooth numbers? So hopefully we all sort of know what smooth numbers are. They are integers where all the prime factors are less than some parameter y. Also, can everyone see my cursor? Awesome, fantastic. Yeah, so it's y smooth if its prime factors are all at most y. And smooth numbers, a couple of examples: 128 is 2 smooth, 60 is 5 smooth. It's also 7 smooth and 20 smooth and blah blah blah. But smooth numbers are they're useful in factoring algorithms, and they're also useful for constructing large gaps between prime numbers. So it's very sort of studying them and studying their distribution is a quite well-motivated problem from a number of angles. So quick notation that I'll use throughout these slides. So this capital P of n is going to be the largest prime factor of n. Sometimes in the literature, you see this as P with a subscript plus. And then if you want to denote the smallest prime factor, you use a minus. That's just cumbersome notation for this purpose. So I'm just going to denote it like so. So P of 60 would be 5. And then the counting function for the number of y-smooth integers up to x is denoted with a capital Greek psi. So psi of xy. It's just counting these integers. Okay, so the first thing I want to talk about is something called de Bruijn's identity, and it's just Bookstaves identity, but it gives you a really nice sort of recursive identity for the smooth the summatory function. Geez, I can't talk. The summatory function for the smooth numbers, just in the same way that you have for kind of like a regular sieving function, because this is a sieving function. It's just sieving out by all the primes that are greater than y, right? So anyways, if I write this quantity on the left, this is all of the integers which have a prime factor bigger than y, or their prime factor is bigger than y. So I'm just going to sort of separate them by what their biggest prime factor is. So if I do this, just sum up over all the primes that are bigger than y, and of course less than x. And then just the sum of the integers which have that prime as their biggest prime factor. Well, just divide it out then. So if I do that, I write n equals n times p, divide out by p. Well, now the biggest prime factor, I could have had repetition. So my largest prime factor can still be p, but it can also be smaller now. The remaining integer part, can be smaller. But what is this? This is precisely just the counting the p smooth numbers up to x over p. So we have this really nice identity over here. So psi of xy is just x minus this thing, plus big O of 1 for the fractional part of x. And again, this is just Bookstaves identity, maybe recast in a slightly different way. So the first thing I want to do is kind of prove a very simple estimate when y is very large. So if y is greater than the square root of x, so in that case, if p is a prime that's bigger than y, then when I do x over p, I'm now less than p, right? X over p is less than the square root of x, which is less than p. So in that case, the p here in the summatory function is doing nothing. It's all the numbers are trivially have all their prime factors less than p because they're just less than p. The answers themselves are. So the summatory function is just the floor of x over p. And if you write out what this is, well then if you rearrange this equation, you put in x over p. This, we get the x here plus a big O of 1, which is absorbed into the error term. And then we have a minus, because we had to subtract this over. And then we have the sum of like 1 over p after you factor out the x, right? So the sum of 1 over p grows like log x. So I get log x minus log y. There's a constant in the asymptotic for the sum of the reciprocals of the primes, but that cancels out. And then the error term is like 1 over log y. Log y has size log x because y is a power of x, essentially. And so we get that if I sort of recast my this asymptotic using this notation, this also I should say there's a big O of 1 term that's giving summed up like pi of x times, and that's giving me x over log x, an error term of that size. So if I use this parameter, this log x over log y, then here I can write down what my asymptotic looks like, and it's something of size x if u is fixed, plus a smaller order error term. And this quantity log x over log y turns out to be the sort of the most natural quantity to work with when you're dealing with smooth numbers. Everything just sort of, you can write things very naturally in terms of this quantity. So this is the main sort of quantity that we'll work with. And so this is saying that if u is fixed and it's between 1 and 2, that's what y being in square root of x to x means, then the smooth numbers, the count of smooth numbers up to x satisfies this asymptotic. And I'll say a little bit more about this later on, so that's why I have it starred. So put this in your brain head place and remember it for later. Okay, so the main thing about this identity, the identity of the Bruijn, is it gives you sort of a functional equation for the smooth number counting function. It allows you to relate it to sort of different values of the function, but it's not quite optimal, because if I look at this, it varies in both of the coordinates. As p varies, it varies in both of the coordinates, right? X over p and p vary with p, and so for that reason, it makes it like not the most ideal thing to work with. It's kind of a pain to work with, and so it would be better if we could sort of make it so it doesn't vary in both coordinates, but maybe only varies in one, and that's what we can actually do. So the identity that I'll use is, I don't know who first wrote down this kind of identity, but I think it's a really neat idea. I'm just going to very trivially say that the summatory function times log x is equal to this thing, right? This is log x minus log n and then plus log n. So clearly this is sort of a trivial equation. And then I'm going to evaluate each of these two sums in a different way. So the sum on the left, the first sum, I'm going to use the fact that log n, I can write it as a divisor sum. I can write this as the sum over all the divisors of n times the von Mangold function, which is log p at prime powers and 0 otherwise. So a standard sort of identity in number theory. And then the second sum, what I'm going to do is evaluate it using partial summation. And when you do partial summation, you write down what it is. The sort of, you get a sum term and then an integral term. But the sum term is actually 0 in this case, because if I put in x here, I get log of 1, and that's 0. So in fact, this is actually just an integral. It is the integral of this thing once you sort of work out what partial summation gives you. The derivative of log x over n with respect to n, is 1 over n, and so 1 over t is here. And then if I interchange the order of summation, because in analytic number theory, you're always summing in the wrong order. If you do that, then we wind up with this equation. And this, notice, if I sort of divide through by log x, this gives me a functional equation, which it's a little bit more complicated perhaps, but it gives me a functional equation for the counting function, which only varies in the first parameter. Y is fixed in all 3 places. And that's a really convenient thing. It makes it sort of more efficient in a certain way. I'm not going to elaborate on that comment because I'm sort of parroting it from some of Sound and Granville's notes. But anyways, one of the things you can do is sort of estimate parts of these trivially. So if I work out what the contribution of prime powers is for powers greater than or equal to 2, you write down what it is, you switch the order of summation back, and then you see what you get. that contribution is big O of x. I think it's actually big O of x over log x. And then the integral contribution, well, psi of t y is trivially bounded by t. And so this whole integral is just bounded by, the integrand is bounded by 1, and so the integral is bounded by x. So psi of xy log x is actually just this very simple thing up to an error term of big O of x, which is fine because, remember, I saved the factor of log x when I divide over. Yeah, the only thing that contributes, sort of, if you've been doing analytic number theory for any amount of time, the only thing that is really contributing is the sum over primes. And this we can actually sort of work with and compute sort of a smooth asymptotic using this sort of identity here. Later on, for a more advanced argument, we will need the full sort of functional equation, but for a sort of preliminary estimate, we can derive one just using this sort of simplified version here. Okay, so let's do that actually. So let's suppose that my counting function, actually, before I move on, I should pause and see if there are any questions over anything that I've said so far.
Yeah, so just roughly, how big should psi of xy be? So like
if u is fixed, so if y is essentially a power of x, psi of xy should be of size x, and the constant depends on u. So it'll be like x times some constant depending on log x over log y, which depends on log x, but if log x over log y is a fixed value, i.e. y is a fixed power of x, then it's only depending on whatever that power is.
Okay, but like as soon as u starts getting...
If u starts growing, then we'll need a different argument, which I will show. So okay. for the first part, I'm only going to assume that y is a fixed power of x, and then we'll start being able to deal later on with much smaller values of y, going down to essentially log x over, or no, going down to something that I'll write down later on. I don't remember it off the top of my head.
Okay, but for now, u is fixed, and so you're saving like 1 log off the main term?
Exactly.
All right.
Yeah, good question. Any others? Okay, so I am going to sort of assume that my counting function obeys some sort of asymptotic, and I want to work out, well, what should that asymptotic roughly be? What kind of features should it have? So let's suppose, I've sort of already motivated u being the natural parameter to work with. Let's suppose psi of xy is asymptotic to this quantity. And for all intents and purposes, let's just make this an equal sign. Like what should this function rho do? What should it obey? Well, I'm going to completely ignore error terms because we're just conjecturing things at this point. And so if I write down what this should be, well, my psi of xy, that's x rho u times log x, this should be, well, what I had before, this thing, so x over p times rho of whatever it has to be, log x minus log p over log y. And so it should satisfy something like this. And this, I should be able to evaluate using some prime number estimates, essentially. And if I do this, if I just use partial summation, then when you do the partial summation, you'll have a term that comes from putting in a y here. So that gives me a u minus 1. So my smooth function is going to be this rho here, or my differentiable function, I should say. So I evaluate it at the endpoint, which gives me the rho of u minus 1. And then log p over log y is log y plus big O of 1. And I'm going to ignore the error term. So my first term should be x rho of u log y. And then once I do my derivative and sort of do my chain rule and everything, then I get an integral like this. Again, the log t here coming from just summing this with a y replaced by a t. Again, ignoring error terms. So it should roughly obey this. But then let's go ahead and change variables because I want to make things look a little bit nicer. So if I change my variables to be t being y to the v, so t is some power of y, and then if I rearrange things, so divide through by x over log x, then rho of u should be, well, just divide through by x over log x. The log y over log x becomes 1 over u. That's this term. And then my x goes away, divide through by log x, but then the change of variables works out so that the integral has the following form, and it's just an integral from 0 to 1. And well, this is actually just has a very simple form. It has this form. And who can tell me how might I go from the left side of this equality to the right side? What's the very simple thing I would do? What's the Calc 2 thing I would do?
Change of variables?
Not quite.
Oh,
Integrate by parts.
Yeah, just integrate.
oh.
Yeah, integrate the rho, differentiate the v. That's it. So if you integrate by parts, everything cancels out nicely, and you get this thing on the right. So let's just define rho to be this function, to be the thing which satisfies this. I also know I have some initial conditions that if u is less than 1, which means that y is bigger than x, then rho should just be 1. I should just be getting everything, like all the smooth numbers up to x, or I should be getting all the integers up to x. So I have this sort of initial condition. And then if I sort of rearrange my equation that I had here, then I have this integral equation. And if you differentiate this and sort of say, okay, well, if I differentiate it and then I take my initial conditions as what they need to be, this is the same as just a differential delay equation, like so. Kind of like what you get when you're working with the linear sieve. If you're doing sieve theory, you get a similar kind of equation. And so this function, the function satisfying this is the Dickman-de Bruijn function. It is the function which governs the distribution of the smooth numbers. And I think, when you first start talking about smooth numbers and then someone just throws this differential equation at you, it's like, well, wait, why? Like, where is this coming from? But if you sort of work through why that is, you see that's exactly what it has to be. Like, it must be this quantity that is modeling the distribution. So it's a very natural sort of function to work with. It arises very naturally from studying smooth numbers. So yeah, I'm just going to let rho be the continuous solution of this. And I want to write down a few properties of this function. So first of all, we already showed, and you can use this integral equation in this initial condition to show that rho of u is 1 minus log of u, as it must be, right? That's what we had before. That was the coefficient of x when y was bigger than square root of x. So rho does indeed satisfy this, that we need it to satisfy when u is between 1 and 2. It actually decays really rapidly, so it's always positive. You can use the integral equation and the you use the integral equation to show that it's positive. And then if I want to show this estimate, this upper estimate, I can just divide through by u and note that the derivative is actually always negative because rho is always positive. So when I divide through, the derivative is always negative. So the integral is just bounded by what it is at the lowest point times 1. And then you iterate that, and that gives you this 1 over the floor of u factorial. If you didn't want the floor function, you could do 1 over gamma of u if you wanted for the gamma function. So it's decaying very rapidly as u grows, like 1 over u to the u roughly. And then finally, as I just said, the derivative is negative. It's always negative. Well, it's 0 if u is between 0 and 1, and it's strictly negative if it's bigger than 1. There are some other properties of rho that you could write down. And I'll write down some estimates for various things later on, but for now, I think this is sort of satisfactory. It's everything that we sort of need. So questions on the derivation of the Dickman-de Bruijn function? Okay. So the thing I want to note is that this argument that I did here, where I just completely ignored error terms, you can do this where you don't ignore error terms, and you can make this completely rigorous. So if you sort of take the right side and evaluate it with rho being this Dickman-de Bruijn function, and then you also compare it to what the smooth function, or what the function counting the smooth numbers is doing, you can prove the following sort of inequality. So that if I look at the difference between these two things, which I expect to be sort of the asymptotic main term, times log x, this is bounded by log p times this big expression, and then plus an error term, which is some constant times x. The constant here doesn't matter too much. It's just some implied constant. But this constant right here is genuinely 1. You can take it to be 1. So if I sort of do this, notice inside here, all of the arguments have x over p that's less than or equal to x over 2, quite trivially, right? P being the smallest prime, or 2 being the smallest prime. So what you can do is basically do an inductive argument and say, okay, well, suppose I've proven some asymptotic for t less than or equal to x over 2, and now I want to prove it for x. Well, just apply this identity, this inequality, and now this means I get to use my inductive hypothesis. And so once you do that, here's the inductive hypothesis that you're bounded by t over log y, this error term, essentially. So you're bounded by t over log y. If you put that in and you write down what your answer should be, then when you evaluate it, log p over p is going to give you a log y, which cancels with this log y. So I get an x, and then log p up to y gives me a y, which is bounded by x, trivially. So my whole estimate here is bounded by x. And so my psi of xy minus x rho of u, for rho of u being the Dickman diversion function, I can actually write down this asymptotic. I should have like a +1 in here in case u is like 0. But if u is 0, go do something else with your life because you're not doing interesting mathematics. So u is positive here, and it will be for us pretty much always. And so the function that counts the smooth numbers up to the y smooth numbers up to x, which is just y to the u. So here, u being fixed, I can write everything in terms of y and u. It is genuinely x rho of u plus some smaller order error term. And it continues to be like that for any fixed value of u, not just for u between 1 and 2 like we had it before. Okay, so this is a fairly sort of preliminary estimate. Now, one thing to say is that this is sort of only a valid asymptotic so long as u is basically constant. If u starts to get very, very large, there's no way this can remain true as an asymptotic, because this is like 1 over u to the u. And so in order to have an asymptotic equality, you need u to the u bounded by log y, which is essentially saying you need u to be constant. Now, it's not quite that. You can have like tiny little bit of growth, but not much. So essentially, if u grows faster than a constant, this is going to be violated and you're sad. So because you don't have an asymptotic anymore. Thankfully, though, you can establish this asymptotic with a much better error term and a much wider range. And that's what we're going to do next. So this is a theorem due to Hildebrand. Uses a very, very nice recursive argument. So this estimate, so I have the main term that I want, x rho of u, and then my error term before this was like 1 over y over log y. Yeah, but now I have an extra rho of u times log u plus 1. And so that gives me a much better asymptotic. And this estimate is actually an asymptotic for a much wider range. So before, let's see, y could essentially only be a power of x, a fixed power of x, which is, x to the epsilon, maybe for some fixed epsilon. But now y is allowed to be something as small as essentially, x e to the power of log x squared. This squared here, this is coming from the error term in the prime number theorem. So you have like exponential of c square root log n. So the 1 over 2 there, when you take the 1 over 1/2, that's what's giving you the 2 here. So you can actually widen this range a little bit. I think Hildebrand in his paper actually has a 5/3 here, because that's coming from like the Vinogradov-Korobov zero free region. But I just chose to write it like this because I think it looks nicer. So yeah, so you can prove this estimate in a very wide range, and we're actually going to do that. Okay, so how do you actually prove this estimate? So the thing that Hildebrand does is he basically uses a recursive argument to bring you back to the situation of u being in 1 to 2, because you understand everything when u is between 1 and 2. And so that's the sort of nice thing about his argument is how it goes about doing that. So let's talk about how he does that. So we start with the better functional equation that I wrote down before. So the integral plus this sum with the von Mangold function in it. So what I'm going to do is I'm going to write down, I'm just going to define a new function delta. So this delta of yu is going to be whatever the error term is in this approximation. So like it's, psi of x, y over x rho of u minus 1. And we want to give an estimate for that thing. And I'm going to define this delta star as just the supremum over all the smaller values of v in here. So basically, if y is fixed, then for u, being, or v being between 0 and u, I just want to see what does this do? What is the biggest value that this attains? Also, I just note that as u increases, this is also a non-decreasing function, trivially, right? A supremum of an absolute value is non-decreasing as you increase the range. So with this notation, let's rewrite this with this. So if we do that, it looks kind of ugly at first, but if you just sort of parse through it, you see you do get exactly what you want. So on the left, if I replace it by this, divide through by x rho of u, and then divide through by the log x, here's my integral. This is the psi of ty times rho times t, and then the t's had canceled. So that's this is genuinely what the integral is. Same thing with the sum over primes and prime powers. With the von Mangold function, it's this sort of ugly object. And then I had a +1 on the left, which I've moved over as a -1 here. So it's this sort of big object. And now I want to try and estimate this thing. We can do it. We shall do it. So the idea is actually to break this up into like 6 different pieces. It sounds complicated, but it's not actually too bad. So what I'm going to do is just write this as the following. It's going to be an integral, which is just going to be this whole integral, an L, which is going to be a sum over basically n, which are large, and then a sum over small values with this multiplied by this thing, and then a sum over small values without this thing, which is going to be like my main term, and then I have the -1 from up here. So as I just said, here's what all these things are. So the I is just the integral expression. L is the sum over a large value, so n greater than y of this thing. S is the sum over the small integers of this expression. And then my main term is the same thing, but it doesn't involve the delta function here. So sort of as one would expect, these first two are going to be error terms. And then in order to get S and M into a right sort of way to estimate them, which maybe it comes as no surprise, we're going to apply the prime number theorem here. So in order to do that, we're going to need to sort of finagle things around a little bit. So I'll show you how to do each of those things. So let's estimate I and L first. And again, I'm going to be very brief in details. I'm just trying to give the main ideas. All of the technical sort of calculations are not, well, they're technical calculations. I'm not going to go through them. We do need 2 estimates. And that is, one of them is just the quotient of the derivative and the function. And this is, you can actually bound it by this logarithmic expression, which is essentially tight up to this power of log. I think asymptotically, this is really like log u times plus log u. So this is a pretty tight estimate. And then what you can do is use the differential equation for rho and essentially iterate it for v. Oh, I should have had a comment in here. V should be between 0 and u. For v between 0 and u, you can give this upper bound for a quotient of the differences. And that's sort of what we want, right? That's really what I have. I have rho of u minus something divided by rho here. So that's, this is a quotient I want to estimate. And it's bounded like this. And again, it's just simply iterating this identity, essentially floor of v times. That's how you prove that. So how do we actually apply these things? So first of all, in my integral equation, I'm just going to do a change of variables. And when you do it, it comes out to this. And then here's the quotient that I exactly have right here, rho of u minus v over rho of u. I just slap this estimate in here very simply. I'm going to estimate this thing just by the supremum, just do it pointwise. So that comes out as the factor out front. The u here is still here, the rho of u minus v over rho of u, that became this factor in the numerator, and then I have a y to the v in the denominator. And then, well, just integrate it. I mean, this is a Calc 1 integral, right? It's some constant, which doesn't depend on v, to the power of v. So you integrate it, what do you get? It's bounded by this estimate in the top divided by u log y. And so this is the sort of savings that I'm kind of looking for here. Okay, so there's the integral done. That's it. That's all we had to do. And for the large values of n, for the prime number sum, it's going to be essentially the same thing. So real quick, how does that go forward? So this was the object I need to estimate, and I'm going to basically show it satisfies the same estimate as my integral. It's bounded by this thing. It's actually bounded by something a little bit smaller. But anyways, if I do this, slap the same estimate and the same sort of thing as before. Here I have my rho of u minus something over rho of u. The log p is bounded by log x, so that cancels out. And then the thing that was like this, if I work out what that is and write it as like p to some power, then here was my v, the log p to the m over log y. If I write out like the thing to the power of v, which involves p to the m, I can write that as p to the some power. And it ends up being this negative power of p. So p to the m times 1 minus beta. So the beta here being the thing that was coming from that estimate we used before. And the thing about this estimate is that in the range of u and y that I wrote down before for the theorem, so y bigger than exponential of log x squared, this, if y is sufficiently large in terms of x, which we're certainly allowed to assume, beta is eventually less than a third. So this goes to 0 as y grows. And so if beta is eventually less than a third, this is eventually like 2/3, like m to the 2/3. And then once you have that, you just estimate the sum as a sum over prime powers. And it's essentially bounded by this. I think Hildebrand uses a 1/6. The 1/6 here is pretty immaterial. You could have said 1/4, and this would be like 1/8. Doesn't matter. It's bounded by some negative power of y, and a negative power of y is bounded by log y, or 1 over log y. So we do in fact have the same estimate that we had for the integral. So that handles the large values of n in my sum over with the von Mangelt function, and it handles my integral. So now I need to actually kind of work on my main term and see what should I be getting out here.
Did you need to say anything about delta star? So delta star is just defined as like the supremum of the error?
Yeah, so delta, yeah, exactly. So of this thing. So I'm just bounding this pointwise by its maximum, which is delta star.
So, but your result in the end doesn't have a delta star. It has some like explicit...
No, sure, but well, the final result is a bound for delta, which is implied by a bound for delta star. Right, trivially. Yeah, so our final estimate is actually an estimate for delta star. And what we'll actually end up doing is saying that delta star is essentially bounded by delta star of y u minus a half. So it's actually bounded by the plus some error term. And then
you're going to like write it, you're going to write it in terms of
a smaller value of delta star, yeah.
Okay.
Or a delta star at an earlier value.
Okay.
Yeah, so that's what we're going to do here. Yeah. So yeah, I'm leaving everything in terms of delta star for the moment, because you'll see that we're basically able to recurse back, and it's really nice. Yeah, other questions? It's good stuff. Okay, so let's work on the main term. So the main term is, well, it's the thing I had written down before. I don't really know why I separated it as S and M. You kind of need to put them back together here. Anyways, this is the term that I haven't sort of dealt with yet. And here I'm thinking of 1 as corresponding to like the main term, right? And I'm subtracting off the main term from what should be like a smooth approximation to it. And so what I'm going to do is I'm going to split this sum, and I'm going to split like 1. I'm going to split the main term, at the square root of y. You could split it at another part, but the argument wouldn't be quite as nice. So here I'm just splitting it right in between, like sort of at the halfway point, the logarithmic halfway point, as it were. And so if I do that, well, my main term, I want to write it in terms of rho. And so if I use the differential equation, which I've not written out correct here, this should be a 1 over u rho of u. That's a typo. If I write out what this is, well, I'm just going to write this as, well, half of the integral plus the other half of the integral. So it's the integral from, again, another typo. There should be a u here. I think there should be, right? I wrote u rho u equals the integral before. Yes, I did. Yeah, so there should be a 1 over u right here, or a u next to the rho here. So I'm just going to split the main term in this way. And again, the idea is that I'm going to recurse backwards by like steps of a half at every time. So that's what the minus a half is going to accomplish for us. And then I'm just going to group the terms here after I split my sum at square root of y. It's sort of easy to see that the terms coming from square root of y should correspond to the alpha of u. And the terms bigger than square root of y should correspond to the bigger terms up here. Of the second term here. So yeah, split S and M at y. And so the thing I get, basically you have to add and subtract the delta star term times alpha, times each of the corresponding alphas. And when you do that and then slap a triangle inequality on everything, you get that this thing you're expecting to be your biggest error term, or your worst or most difficult error term to handle, is bounded by this expression where you have a delta star with these alphas. And then you have a similar thing as before. We factored out a 1 plus delta star times two terms that involve, that are like differences of main terms. So we expect this to be a main term, which is well approximated by alpha, and this is a main term well approximated by 1 minus alpha. These things are what you use the prime number theorem for. So when you do this, I'm not going to go through the technical calculation. It's actually not that long, but nevertheless, I don't really want to do it. When you do this, you use the prime number theorem, and you get the same estimate as we had before. So I have a 1 plus my delta star, and I want a 1 over u log y here, and that is indeed exactly what I'm able to get. I have a 1 here because the invocation of the prime number theorem, that is what is governing the range of y in your theorem. So how small can you take y depends on how good of an error term in the prime number theorem you have. So that's kind of where that restriction comes in. So let's simplify what we had before. So my error term is bounded by this expression here. So my delta of yu is bounded by delta star of yu in this alpha, and then a similar sort of thing, but shifted back by a half. And then my error term is just 1 plus delta star over u log y. Okay, now I'm almost ready to apply a recursive argument, because you can kind of see like, okay, well, maybe like this is bounded by like a half of like this or something, and I can like creatively subtract it over and multiply, and then I have like a nice inequality that allows me to recurse down or something. But these alphas are kind of like messing you up. So the thing to note is I have this identity. So alpha of u, I can just go back and sort of say what this is bounded by. This is bounded by a half, if you just sort of work it out with a u here. This is bounded by a half. And so this first term is positive. Delta star is monotonic, so this is certainly also positive. So this whole thing is positive. And what I can do is then just add it to my upper bound, trivially, right? I can certainly just add a positive number, and my upper bound is still an upper bound. But when you do this, what happens? Well, things cancel out nicely. And what I'm left with is that delta is bounded by 1/2 of this difference right here. And now what I can do is sort of try, actually, should this be a plus? I think this should actually be a plus right here. Again, typo, really bad at those today. Yeah, so this is a plus, not a minus, my bad. And so what you do is you say, okay, well, this is essentially uniform in the variable u. Well, it's not quite that, but essentially I'm going to replace delta here by delta star. There's a slight technical argument to say why you can do that. I'm going to ignore it. So this you can think of as just delta star on the left. Well, subtract over the 1/2, multiply by 2, and we get this expression here. So my delta star of y and u is bounded by delta star of y and u minus 1/2 plus this error term here. So now I can iterate this, and that's going to give me my final estimate. So let's go ahead and do that and conclude the proof real quick. So if I iterate this, basically I'm going to shift back by steps of 1/2 until I force my second argument here to be in 1.5 to 2. So that's what I get. The number of times you have to iterate it is the floor of 2u minus 4. Cool. U being bigger than or greater than or equal to 2, sort of by hypothesis. And then you get this estimate here. So this big O term, I can bound this. The numerator, I'm just going to take it as just the worst case when u is just u or u minus k over 2. I just take the k equals 0 case. It's certainly bounded by that. My log y, that comes out here. And then I have the sum as k goes from 0 up to something of size u of u minus k over 2. And when you compute what this is, that's a quantity of size log u. And you can sort of already see the shape that we're getting. We're getting a log u over log y. And the thing about iterating all the way down to this case is we know what this does in this case. We know what this error term is. It's bounded by, well, log u naught. Well, it's really bounded by 1 over log y, because log u naught is essentially just a constant because u naught's bounded by 2. But anyways, we certainly know this estimate from our calculations before. So when you sort of group all of these things together, if you were to iterate sort of this identity, so this being bounded by essentially this thing, what you get is basically a geometric series of decreasing terms. The terms are getting smaller and smaller. So it's bounded by the largest order term. And we put a u plus 1 here just in case u is like less than 1, because we're going to think trivially. So if u is bigger than 1, this is certainly just a log u instead of a log u plus 1. But anyways, just a simple technicality. And there we go. That gives me the theorem, right? The error term, my delta, is bounded by delta star, trivially. And that's bounded in magnitude by this log u over log y. And that proves Hildebrand's theorem. So really, really nice argument. When I was first reading through this, and he got to this step, like right here, I was like, bruh, this is just really, really nice. I thought this is just a really beautiful inequality, in my opinion. So yeah, I've got one more thing to talk about after this, but I'll go ahead and pause and see if there are any questions. I don't have my water bottle nearby, I'm sad. Okay, so the last thing I want to talk about is a sort of interesting behavior when this u value gets like really big. So before we were sort of restricting u to be basically bounded by log x over log y, and y being bounded below by some exponential of log x squared. So when y is like really, really small, or u, which means u is really, really big, the counting function, basically it goes through a phase transition. So now this is okay, I'm going to skip this. I don't want to talk about it. Yeah, so there's a phase transition when y is equal to log x. So yeah, there's a theorem of de Bruijn, which I'll prove for you. It's actually a very simple theorem to prove. It won't take but a couple of minutes. So as y and u go to infinity, the log of the counting function is asymptotic to this expression. And you can sort of see that depending on whether y over log x goes to 0 or it goes to infinity, that changes the asymptotic, right? If log x over log y goes to infinity, this second term dies away. So I'm just asymptotic to this thing. But if y over log x goes to infinity, this first term dies away, and I'm left with this asymptotic. So it really depends on if y is greater than log x or less than log x, or what their asymptotic sort of differences are. And I should say that this theorem of de Bruijn that we're going to prove, it actually recovers a classical result of Erdős. So if you just set y equal to log x and work out what this is, then log of the counting function, where I'm looking at the log x smooth numbers up to x, this is asymptotic to log 4 times log x over log 2x, or log x. Also, I realize sometimes I've been saying log 2x. Hopefully it's been clear that I mean log x in that case. I don't work with different bases, at least not in this research. Okay, so how do you actually prove this? So this is an upper and a lower bound. So we're going to prove that it's bounded below by something of this shape plus an error term, and then bounded above by something of this shape plus an error term. The lower bound, super easy. I mean, it takes like 10 seconds. And when I first read over it, I was like, that's really clever. Upper bound is slightly more complicated, but not really that much. So let's do it. So if I have an integer which is less than or equal to x, and it's a y smooth number, then let's just take the logarithm of that number and write it in this form. So it's equal to log p, the sum over all the primes less than or equal to y, log p, times these variables, which are just non-negative integers. They're mostly 0, but they're non-negative for some of them, right? So certainly this is true, and it's bounded by log x. So for this sort of equation, I just need to count the solutions to this equation. Well, I can more easily count a subset of the solutions, namely those given when this inequality is true. So if I just take log p to be the maximum of what it can be, log y, divided over, this inequality implies this inequality. So the solutions to this are a subset of the solutions to this. This is the stronger condition. But this, I know how to estimate this. This is a simple combinatorial object. I just want to, I have, pi of y, non-negative integer variables bounded by some thing, which these are integers, so I can just take the floor function of this. And so this is a pretty standard sort of combinatorial thing. So you first, you set this thing equal to some integer less than this, and then you sum up all the solutions. This is like introductory probability theory combinatorics sort of stuff. And the number of solutions to this inequality is exactly this number. So this is u on the right here. I have pi of y variables. And so it is just pi of y plus the floor of u, choose the floor of u. Now this is a binomial coefficient, so I can write it out in terms of factorials. And what I can do is take those factorials and apply Stirling's formula to them. So if I do this and I just apply Stirling's formula, I'm going to again ignore some error terms, and I get this expression. So it's very symmetric. It's just the argument times log of the argument, and then minus the top argument, and then minus the same thing, but with the individual arguments on the bottom. So Stirling's formula gives you precisely this. I'm going to rearrange this into the very suggestive form like so. So you split this sum up and then subtract like terms. And this expression here is just equal to this one. And now what do I need to do to get an asymptotic? Well, I can remove the floor brackets with a small error term, and I can write pi of y as essentially y over log y with an error term. But when you do this, you get precisely this estimate. I mean, it is exactly the thing that we had before. It comes out almost just like, it's just completely natural how it comes out. This is like the thing you must get from this argument. So that immediately tells you that, and remember, this was a lower bound, so we're giving a estimate for a subset of the solutions. So this immediately gives us the lower bound that we wanted. So now I need to get an upper bound of the same shape. Again, I'm sort of ignoring error terms here because I just want to illustrate main ideas. So I want to get an upper bound now. And to get an upper bound for smooth numbers, we can use Rankin's trick. So this is a pretty classical trick in analytic number theory. So what I'm going to do is just bound the counting function by, instead of summing up to x, I'm just going to say, okay, well, I can sum up all of these things where I raise, instead of taking 1 is bounded by x over n to the sigma when n is less than x, and then 0 is bounded by this because this is positive when n is greater than x. So this is certainly an upper bound. And the reason for doing this is now a multiplicative object. This is equal to x to the sigma, just factor it out. And then I have a product over all the primes, well, just what it must be. It's the local factors of the zeta function. And so what I can do is I'm going to take a logarithm of this. If I take a natural logarithm, this splits up into a sum, and then a sum of like sigma log x plus the sum over the primes. And then the sum over primes, I can use just partial summation. Again, this is not correct as I've written it. There's an error term here, but I'm going to completely ignore it because I get to. Just illustrate ideas. So the logarithm of this is bounded by, yeah, sigma log x plus the sum over the primes, which after partial summation is essentially this thing right here. So the log t basically accounting for the density of the primes. So how do I choose sigma to optimize this thing? How do I actually minimize this function? Well, to do that, first I'm going to note that if I choose sigma greater than or equal to 1, this bound is immediately trivial. If I choose sigma greater than equal to 1, this is x times something which is log y by one of Mertens theorems. And if it's greater than 1, then this is just greater than x. So I don't want to choose sigma greater than 1. So sigma should be less than 1. And if sigma is less than 1, well, I need to minimize this right-hand side. So let's apply calculus, minimize with respect to sigma. So differentiate with respect to sigma. It should satisfy this. I want to find the sigma, which makes this true. Here, my integral is going down to e because it's a convenient value. Again, there's an error term, but we don't care about it. So my sigma should satisfy this value. And this is like a little bit messy to sort of solve. So let's think like, how can we simplify this? So since sigma is less than 1, when I integrate this, I get basically a positive power of t, when I apply the inverse power rule. So the main contribution to this integral should come from t around size y, right? So I'm actually just going to replace t by y in this integral and see what happens. And I'm going to choose the sigma, which satisfies this. So if I replace t with y here, I get an integral which doesn't depend on t. So it's like it's of length y, and then divided by whatever the denominator was, which was I chose t to equal y. Again, I'm not choosing the exact optimal sigma. I'm just choosing something close to it, which is all I need for this to work. And if you work out what sigma has to be, well, you can already sort of start to see the shape that you want to see. Sigma should equal this sort of expression here. And when you actually plug this in and you work out what this upper bound should be, again, ignoring error terms and being rather informal, this integral that we had on the right above, it's equal to this expression involving the logarithmic integral of y. Again, we're going to use the prime number theorem. That's y over log y. This log of 1 minus 1 over y to the sigma, if you put in this sigma here, it just simplifies to this. This is just a calculation. But yeah, this sigma, put it in here, this factor equals this factor. And then I have this upper bound. And if I put in what sigma is, which was this, if I put in what Li of y is, which is y over log y, essentially, I get exactly the same thing. So that gives me the same upper bound. So again, very simple proof, very simple ideas, but it sort of illustrates this very interesting behavior that the counting function for the smooth numbers exhibits, which is this sort of phase transition. Questions on the proof here of this result? Okay, so the one last sort of set of comments. So I've shown you that this has this like phase transition. Its asymptotic behavior changes around log x. Why? Like, why should the asymptotic behavior change? The main reason is that if y is really small, then the main contribution to the count of the smooth numbers comes from products of small primes to very high powers, as it must come from that. That's the only thing that can contribute to the main term. And so because your main term is coming from products of small primes, it's very sensitive to the irregularities of the small primes. So yeah, in this case, you're basically just, because you're not being able to see all the primes in aggregate, essentially, you're really sensitive to all these like weird irregularities that happens among small primes. And in fact, you can quantify this. So there's a theorem due to Enola. I don't actually know if that's how you pronounce this name. I'm guessing so. But if y is very small, so this is like way outside of the range that we dealt with in Hildebrand's theorem. If y is like bounded by square root log x, then in fact the count of the smooth numbers is actually asymptotic to this. And you can see it depends very strongly on the distribution of the primes of the small primes, because it involves this product over the small primes. As y increases, this product becomes more and more well behaved. But if y is not big enough, this product and these sort of pi of y terms here, they're not well approximated by smooth functions. They are genuinely sort of erratically behaving. And so that's why you have this strange sort of shift in behavior, is you have the irregularities of the small primes, coming in and ruining your day for you. The proof, I'm not going to go through the proof of this, but it's basically a more careful version of this counting argument that Bruijn does for his lower bound. So yeah, that's everything I wanted to share with you, all the cool stuff I've learned about smooth numbers recently. So I hope you all learned something and enjoyed the talk.